So with that, I'd like to introduce the first speaker of our session, Steve LaValle. He's a professor of computer science at University of Oulu, and you probably know him for his work in motion planning and virtual reality. So Steve, please.
Okay, thank you very much, Kevin, and thank you very much to the organizers. Thanks. I appreciate very much the great honor to speak here. I decided to frame this talk mostly around my book, which was written mostly about 20 years ago, which I surprisingly realized is half the lifetime of ICRA itself, so that it's right about the midpoint. So if I go through like that, Lydia Kavraki gave a great overview of history of motion planning, so I'll just be very brief. I think a lot of it goes back to Nils Nilsson and the work at Stanford. A lot of things like A-star search, visibility graphs, strips came out of that. And if you look at several decades of motion planning algorithms, things went from grids, logic-based planning, to what I call combinatorial or exact motion planning, and then sampling-based motion planning, which is mostly what's used today. And as a couple of people mentioned, Matt Mason mentioned this, Lydia Kavraki as well, the Lozano, Perez, and Wesley paper was very influential in getting us all to think in terms of information, or in terms of configuration spaces, which enabled us to unify everything that we're doing with our algorithms. So very different problems. Manipulators or mobile robots all kind of look the same in configuration space. Some differences come up, but it's the right kind of abstraction. So just going over combinatorial motion planning, cylindrical algebraic decomposition, employing the tools of computational real algebraic geometry was the first complete method to solve very general motion planning, described semi-algebraically, where the primitives are described that way, the kinematics, everything. The best general known algorithm is Canny's roadmap algorithm in terms of complexity, roughly speaking, singly exponential in dimension. There's actually been some recent implementations and practical developments in that area due to some people doing improvements in algebraic computation out of France. So it's one piece of work you might want to look at. I believe it can be applied to like 6DOF manipulators and such like that. So don't think that these older methods are just not good. They just didn't have good computers at the time, for one thing, and a lot of things have improved since then. A little bit about my own background. So I was a graduate student at the University of Illinois, Urbana-Champaign, and Seth Hutchinson was a brand new professor there in 1991, and he started this motion planning class. Jean-Claude Letombe's book was brand new. I think he even got a hold of the notes early on that. Jean-Claude visited and such, and that was very inspirational to me. And I also had Seth as my PhD advisor. I was his first PhD student. He was a wonderful advisor and was really helpful in helping me to cure my imposter syndrome, which I haven't fully conquered, but it was very important. And also an interesting trivia point, both of our fathers had the same profession. Let's see if anyone, you can guess what it is. I won't tell it here, so let's see. So one of the big methods at the time that was really prominently featured in the book is the method of Barakhan and Letombe, randomized potential field planner. It was using the Osama Khatib potential field idea mixed with random walks to get out of local minima, to just aggressively, in a gradient descent way, go to the goal. And so that was very influential, but everybody knew it involved some parameter tuning. It was very unreliable. You run it each time and kind of hope for the best. But it was very impressive that it solved high-dimensional problems, like 6 to 10 degrees of freedom. So that was really impressive. But the thing that bothered me as a young student was I thought, well, why are we always using kind of recycled things? Like there's, Brownian motion is the base. It's very important in physics for particle motion in a gas, and that's why we're looking at random walks. But I thought in motion planning, you can jump around from place to place for free because it's all in the robot's brain. You're not actually moving the robot to do that. So I thought even back in the early 90s, there needs to be some kind of space-filling tree. So I'm going to run some code that I wrote, hopefully. So if you just do a random walk, it looks like this, right? You just get some kind of uncontrollable thing, and it's used for all kinds of, escaping minima and doing whatever other kinds of things. But when I got to Stanford in 1995 as a postdoc in Jean-Claude Letombe's group, I met James Kuffner, a brilliant young student, PhD student, and we started goofing around together, trying out different kinds of ideas. And this jumping around for free, one of the most natural things to do is take this and just jump to any vertex in this random walk and then go in a random direction. And that ought to make shorter paths, and it ought to just kind of nicely explore. So let's see what happens if we do that. Pick a point, pick a vertex at random, go in a random direction. So if we do that, it does that. I thought it would uniformly explore the space nicely, but it just likes to just keep going over the same, just makes a hairball in the center, and that's about it. And it gets more and more concentrated as time goes on. And then in 1998, I was a young professor at Iowa State University, always thinking about these problems. And I was driving along in the car one day and just had this insight, wait, the space has to pull on this tree thing that you're making for it to work. It's like as if little advisors pop up around in the space and say, drive towards me, and you find the nearest point in the tree and then pull it. And when you do that, then it looks like this. I ran home that night in June of 98 and just hacked this up, and I was like giggling by about midnight, and this thing just made beautiful pictures that were better than what my imagination was for this. It makes these just really nice stochastic fractals. So I was so excited, I reconnected with James the next day, and we quickly raced in a couple of months for the ICRA deadline, which became the paper that won the ICRA Milestone Award in 2019 for most impactful 20 years later. So it was really an exciting time. So let me go over some things here. Come back to we can Control L, and I go back. So we use this for planning, and we have a couple of papers. The ICRA paper I mentioned turned into IGRR, and then RRT Connect, which I believe is the most widely used motion planning algorithm to date, and that was presented at the next ICRA. And the first version was for kinodynamic planning, which I'll talk about, and then it was done for regular planning. I also did some crazy stuff after this. I decided to kind of attack the foundations of randomized path planning. People were very interested in Monte Carlo and random things, but in digging more deeply, I discovered that deterministic methods are actually better than random, and that really shocked people. And that's what Ken Goldberg was referring to in the panel on the first day when I kind of asked him confidentially, should I be doing this kind of work? Is it suicide career-wise? And so, in any case, in this paper with Brannicky and my student Steve Lindeman, we got people to kind of rename the field from randomized path planning to sampling-based motion planning, because the idea is that you're sampling, you have a dense sequence of samples that have kind of nice uniformity properties, and it turns out there's deterministic sequences that are more uniform than random. Random points have to be sloppy in some way, and you don't want to pay for the sloppiness if you don't need it. So then the field of sampling-based motion planning then came into full swing. Wonderful collision detectors. I wish I could go into all the literature. Lydia gave great talk and slides on these kind of things. There's probabilistic roadmaps as well, which she covered nicely. And I'm going to kind of skip over the details of that. One development after my book that I was excited about, I served on Sartaj Karaman's PhD committee, RRT STAR. And then there was a whole slew of very interesting papers and works on asymptotically optimal sampling-based motion planning. So I wish I could talk about those things, but won't be able to. Then going off in different directions, there's planning under differential constraints. So let's go away from the basic path planning problem. So not only do you have global obstacle constraints, but you have differential constraints, which are nicely expressed as a control system, which can be done in configuration space, or you can go up into a higher dimensional phase space, typically 2n dimensional if you want to do acceleration-based inputs. So you're in a higher dimensional space, and then these constraints, due to under-actuated systems, may become non-holonomic. Jean-Paul Lemond, we all miss him dearly. He was a good friend, and I consider him to be the pioneer of non-holonomic motion planning. So you have these kind of differential constraints like this. You cannot just simply move sideways with a car at a local level. The RRT, as I said, originally was designed for dealing with differential constraints. We could do things like try to drive a car in a parking lot with obstacles when it can only go forward and only drive left, and you just have a little bit of steering control. I think that would be very hard for a human to do, by the way. I've never tried it. But there's one of James Kuffner's great thing. We did a 12-dimensional state space flying an X-wing fighter on the moon with obstacles and these kind of things for old work. The motion primitive problem becomes very important here. There's a two-point boundary value problem that you don't have to solve too many of them here, but you have to do some of that. And it's generally, whether it's motion primitives or steering methods, as they're often called, there's been a lot of work on that. One of the first ones was Emilio Frizzoli. He started using it in his PhD thesis a few months after we came out with the RRT. And then a whole bunch of people in aerospace and control have used these so-called kinodynamic versions, which you can also call trajectory planning, depending on whether your background's control or algorithms. I didn't do any work on RRTs for almost 20 years, but then my son Alex got me really excited about it again. And Bashak, an excellent researcher in my group, who's now starting a faculty position at Maastricht University here in the Netherlands. And we did some work that made that original kinodynamic RRT about 1,000 times faster with some new steering method for array of double integrators. I can't go into the details here, but I encourage you to look at that. Then there's feedback motion planning. I named this chapter in my book for the case where you can't predict where you're going to go. Of course, everyone knows you probably want to use a feedback controller anyway, so why not just make a feedback motion plan so at every point in the state space it tells you which direction to go. Student Steve Lindeman did some nice work for his PhD for that, where you can take any cell decomposition, say it's a convex cell decomposition or a cylindrical algebraic decomposition, and you can throw a smooth, almost everywhere, vector field on that quite simply, he had this great idea of just using bump functions, which he learned in differential geometry class. And it's very simple to just smoothly blend. You don't have to go through Lyapunov functions or Riemann Kodachek navigation functions, who, by the way, their work I think was the first of this kind of feedback motion planning. We did some work on sampling-based feedback motion planning, and I should point out that Russ Tedrake and his group did a lot of work like LQR trees and some recent work on visibility-based feedback motion planning as well. Interestingly, going all the way back to my thesis work, I was doing in the early 90s, I found Bellman's equation and value iteration. I was going to the library, found one-dimensional numerical value iteration papers from the 1960s and tried them out in the 90s, and we could solve problems like this, calculating optimal cost to go functions that are for stochastic non-holonomic hybrid problems and do feedback planning. So all that stuff worked in my thesis. Nobody seemed to understand it too much at the time, or it didn't get a huge following. But a lot of these things are called reinforcement learning now with an extra learning part put in. But a lot of these things have been around for a long time. All right, let's see. I'm going to run out of time. Oh, no. So this is the last part of the talk, which is what goes into a robot's brain. So I gave these in terms of configuration space and state space, but I really want to think about what's really the minimal thing that goes in. We don't need a Cartesian theater in the robot's brain. We don't need a digital twin or a deep network necessarily, but it could be something else that's quite small. I'm very inspired by the work of Matt Mason, Mike Erdman, Ken Goldberg, a lot of people towards minimalism. I'm going to have to skip across these pretty fast, but basically there's an external and an internal world, external world and internal, let's say, information states for the robot. It's a coupled dynamical system, and what we want to do is minimize the kind of information transition system that's inside of the robot. And by information, I mean in the von Neumann sense that came out of game theory, not in the Shannon sense, which came later. So no bits, no entropy. This is something else, and something more basic. So we have these kind of information states based on histories, and we want to map them down to something smaller. The Kalman filter is a classic example of that. We have some recent paper that in a very general setting, just general ZF set theory and mappings and stuff, even more general than topological dynamics, a minimal kind of information transition system for a given task always exists and is unique. So that's been some recent works that we've done in our group. And the trouble in general now is to find the right minimal space. We did something called gap navigation trees, which is one good example of that, but where we show that you can do distance optimal navigation without measuring distances. We even went down to crazy things like weasel balls that have this kind of mechanical so-called intelligence, let's say, by doing very billiard-like kinds of motions. And we showed that they can achieve all kinds of tasks in spite of having only a single motor that goes at about 2 hertz with no sensing or computation. We even have a recent paper that's related to that at Wafer in 2 weeks that introduces the notion of universal plans, one plan that solves all planning problems deterministically. So that's a bit of a shocker, and I just throw that there for a hint. Some final things I'll say. Just general trends. I've seen things go from more diversity of thinking to more monoculture. There's a lot of reasons for that, but I don't have time to go over that. There's bigger and bigger hammers, and robots do much better things than they could 30 years ago. But I fear that the interest in mathematical and algorithmic foundations might be slipping a bit, and that makes me a little sad. I worked on the Oculus Rift, doing consumer product development. I've gone all the way to the mathematical end of things, and I find these foundations kinds of questions, mathematical foundations and algorithmic kinds of questions, very interesting. Feedback planning's going to continue to grow. I love this work where RRT Connect is implemented and works in tens of microseconds from Kavraki's group. And I think we should be working towards an improved understanding of what belongs in the brain. And these minimal brains are the opposite of things like digital twins and deep learning brains. And thank you to all my sponsors, students, collaborators, and organizers.
All right, thank you.
All right, I went too long.
Any questions? Questions from the audience? Right up front here.
Thanks, Steve, for
Yes,
this tour of the history of motion planning. In the beginning, you said one thing that struck me. You said that that configuration space is a representation that unifies all of these problems.
Mm-hmm.
In machine learning, you have this field that's called representation learning, which is making basically the assumption that you can solve complex problems if you have a task-specific representation. So that seems to be a little bit of a contradiction. And could we make progress by having task-specific configuration spaces?
Yeah, so let me say, so the configuration space was the unifying notion for the complete model needs to be in the robot's head for that assumption. And then for the information space part, we remove that assumption. And we ask, what are these? So these minimal structures that I'm talking about, they're information transition systems. It's essentially a discrete time dynamical system that models the robot's brain, which is really a computation block, let's say. And so that's what we're getting at. And we're saying these minimal structures for a given task, like clean the floors or whatever it is you want to do, these minimal structures in fact exist, and it's for us to try to find them. Whether we can do it autonomously or we use our own brains to find them. We've done a number of these over the years, as have Jason O'Kane and Dylan Shell at Texas A&M and a lot of other people. So I think I don't see a contradiction. It's just the assumption was like a Cartesian theater needs to live in the robot's brain during the motion planning days. And the configuration space unified things so that you don't have a motion planner for manipulators and a motion planner for humanoids and a motion planner like that are completely different, right? They're designed on the same principles now. So it's unifying in that sense. But for unified brains, then the information space is the right way to look at it. But we can call it other things. I don't like to use the word representation, but I'm kind of an activist philosophically, but we can go into that. But.
Okay, with that, we'll save future questions for up in the speaker area on the third floor, and join me in thanking Steve.
Thank you all very much.